Welcome back. We will start lecture 14. We are shifting gears, as I said just before the break, in that we have already covered all the basics of how to analyze circuits. And you know that has involved the basic laws of circuits, but also some systematic ways of simplifying the way we deal with them. And the basically general idea of the second half of the course, which we'll start today, is electronics. And this is going to be really an introduction to electronics. You can do many courses in electronics. And by that, I mean doing circuits with electronic component and devices. And what I have listed here, diodes, transistors, and op-amps, are where you start things. And there is other things, and some of which you can think of as variations on these themes. And from the outset, I'd like to point out that electronics is a lot broader than what we introduce here, right? This is really just to give you a general flavor. And some of you might go on to more advanced courses on the topic. But so anyway, what we'll try to cover during the next few weeks is really an introduction to these devices as far as their behavior in circuits is concerned. Because you can do, again, quite a few courses on how these devices operate. So if you look at inside a diode and see how it's made and the physics of that operation, that's quite a broad topic. And even to, if you want to start from scratch, from introductory quantum mechanics, just to do the bare minimum of introduction to quantum mechanics and solid state, to go through the shortest path to see how a diode operates, the physics of operation of a diode, would be almost a course. You could maybe do it in half a course, but still, it's a very big topic. So what we are going to do is not so much of a discussion of the physics of operation of these devices, but seeing their behavior in circuits and looking at a particular few applications. Now, depending on how things go, and if there is a little extra time at the end, we'll try to maybe look very briefly at a high level at the physics of some of these also. Okay? But really, the emphasis is on circuits. And I'd also like to make a distinction here that diodes and transistors are individual components themselves. They're elements like a resistor, like a capacitor, with a different structure. An op-amp itself is a circuit. Now, you buy it in a package these days, and from the outside, it looks like a small component. But inside an op-amp, there are many transistors and other things, too. So while from the circuit level point of view, there is great similarities, I'd like you to keep that in mind, that if you actually open any of these up and look at them under a microscope, they look very different. Okay? So with that brief introduction, I'd like to get into diodes. And I'd like to start with a question, something that I'd like you guys to think about a little bit. So diodes. Think about this problem. If I have an AC voltage, and I know we are not doing a whole lot on AC this term, or haven't been so far. We'll do a little bit. But you have seen some. If I have something like this, assume that this is a sinusoidal voltage as a function of time, a sinusoidal signal. So this is something that you would get from the outlet on the wall, right? What is the average of this function over time, the time averaged? 0, right? If you take one cycle, the time average is 0. You have the positive area and the negative area, right? Now, I realize you haven't done signals and systems yet, so you might not be thinking in these terms. But in fact, if you have a signal in general with many components like this, many different frequencies, there's also one component with 0 frequency. That's the DC. That's a constant signal. Okay. If I was interested to start from something like this and create a voltage signal that had a DC component, namely that had a constant, a non-zero average, how should I go about it? Can you think about, based on everything that you've learned so far, designing a small circuit that will take something like this as an input and give me an output that has a non-zero average? Can you think about that for a few minutes? So you have a bunch of elements you have worked with so far. Use any of those and try to see if you can design a small circuit that takes something like this as an input and gives me an output that has a non-zero average. Now, if you're wondering why this matters, for instance, you have a power supply that charges your phone, gives you what? A few volts DC output, right? Similarly for many other devices. Well, if you wanted to make a power supply, a DC power supply, you would want it to have a constant output voltage, right? So I'll repeat the question if it wasn't clear. I'd like to design a small circuit using any combination of components that you have learned so far that takes this as an input voltage and has an output voltage. So on one side, this goes in between two nodes or two terminals. On the other side, there's two terminals that gives me an output voltage that's a constant DC. Would anyone like to suggest something? And by the way, if you've seen it, if you know a standard circuit that does that using diodes, please don't mention that for now. I'd like to get people thinking based on the things that we have seen so far. Okay, so based on the things we've seen so far, any suggestions as to how to go about it? So I really like that. The suggestion here is we have this signal that's half positive, half negative in time. And, well, because of that, the average is 0. But what if I could somehow get rid of, let's say, the negative parts, right? Then if I have left only the top part, the positive part, well, the average of that, I think you would agree, is some positive value, right? If you take the integral over this area, or over this time, and you get the area, well, that's a positive value. So if I could somehow throw away the negative half. And so you're saying, if we could have a switch that could control things such that when, let's say, when the input is negative, the switch disconnected, right? Is that what you're saying? Yeah, so let's see, for example, a simple circuit where this is my input. So this would be V, let's call this V in with some amplitude V naught. And so this goes inside a box. And this is V in between the two inputs. And this is how I've defined my polarity. And now imagine on this other side, I have a capacitor. And I look at the voltage of this capacitor as the output, as a function of time. Now, if I connected this directly, well, I think you would agree with me that the capacitor would just charge and discharge with that voltage, right? You're just varying the voltage across the capacitor. V out is directly equal to V in. But what if I put a switch in here and I connected the switch when the input was positive? Okay, during this first half cycle, if between, so if we call this the origin of time, and this is 1 cycle. So if I turn on the switch, or I close the switch, between time 0 and big T over 2 during the first half cycle, well, the capacitor will just charge with that input voltage, right? What happens if I disconnect the switch right at this point, at point T over 2? If I disconnect the voltage, I disconnect the switch, what happens to the voltage of the capacitor after that? So I have closed the switch for the first half cycle. And I've reached this point. What happens to what's the voltage of the capacitor at the output? 0. What if I keep this on only for the first quarter cycle? What happens then? The capacitor voltage reaches this max value, V naught, right? And then I disconnect the switch at T over 4. The switch is open. What happens to the capacitor after that? Does it discharge? No. It's not connected anywhere, right? So a capacitor that you've charged and not connected anywhere will stay, will retain that charge. Now, of course, in practice, there is always leakage, so, through various paths. But an ideal capacitor on paper will not discharge. So it will have a constant voltage, V naught, across it, and that will be it. So you have, so if you could do this, if you could time this properly. Now, what is the frequency of the AC signal in our electrical system? 60 hertz, I think. So that would correspond to a period of 1 over 60, right? That's a little less than 20 milliseconds, right? So we're talking about a scale of several milliseconds control. So if you could do this fast enough and close the switch at time 0, and after 6, 7 milliseconds, whatever point T over 4 is, disconnect it, you would see that output voltage, that constant output voltage on the capacitor. Now you might say, well, that's good. And that is kind of the essence of what we are going to be discussing for the next couple of weeks. I think you would agree that it's not practical to put someone in charge of closing and opening that circuit like that. So that's one issue we have to deal with. Of course, you might also say, well, it's good that I have charged the capacitor. Now, how useful is that? So let's say if I connect this capacitor now to charge something. So I want to use the charge stored in this capacitor to charge my phone, right? To use this as a power supply. Well, as soon as you start charging your phone, you're giving the capacitor charge to your whatever circuitry in your phone. And so it will then start discharging. So if you really wanted to use this as a almost DC power supply, so if you connected the capacitor to some load on this other side, so instead of just leaving it open, if you actually had something that you wanted to provide this voltage to, and so this is your output voltage now, you could do this for this quarter cycle. The capacitor would get charged to that value V naught. And then you would disconnect the switch. But now the capacitor is going to discharge in this load. So that's it's OK. You're providing some current to that resistor, to that load. But it's not going to last long, depending on the RC, time constant, in this circuit, right? So if you wanted this to keep going, you would have to hire that person indefinitely so that they turn on the switch every time during every new cycle for a certain period of time to recharge the capacitor. right? So this is the essence of the circuit that we are going to try to analyze in steps over the next couple of lectures. And the key element that allows this is a switch that acts, as you said, somewhat automatically, rather than having to do it manually. Okay? This is one example of something that a diode does. And so this is really just a very brief intro. We'll analyze this in great detail. Okay? And so basically, through this exercise, we'll go through how to build a DC power supply. And this is something that you can literally build. And you will build examples of these circuits in the lab. So you will see it in operation. Okay? But just to give you a high-level overview. So with that, let's look at the current voltage characteristics first of a resistor. So we've seen this kind of graph a lot so far, voltage versus current for a given device. And so I'll plot that for a resistor. In this case, I'm more interested in plotting the current versus voltage rather than the other way around. Doesn't matter, same thing. For a resistor, we know that voltage and current are proportional. And the graph goes through the center like that. The slope of V over R, the slope of V over I is resistance, right? Again, in this case, it's plotted in the inverse order, I versus V, but same idea. Okay? Now let's think about a switch. What was a switch? A switch was something that when you connected it, it would act as a short circuit, right? So basically, no matter what current went through it, there would be no voltage drop across it, right? If I wanted to talk about the switch as a resistor, what is the resistance of a switch when it's closed? It's 0. No voltage drop, regardless of the current, when it's closed, right? On this graph, if I wanted to think about lowering this resistance, which way should I shift this line? Which way should I rotate it? If I want to lower the resistance, counterclockwise. Yeah, right? So if I go from here to here, that would be corresponding to lowering the resistance. So I could do something like this. For instance, this would be a lot lower resistance. If this has R1, if this is R2, R2 is less than R1. An ideal switch, we would rotate this so much that the resistance becomes 0. It's basically a line on the vertical axis here, right? 0 voltage regardless of the amount of current. And that's when the switch is closed, of course. What if the switch is open? What is the relationship between voltage and current when the switch is open? There's no current, regardless of what voltage difference you have between the two ends, right? You can, for an ideal switch, you can apply as much as you want, and there's no current going through. So that would be corresponding to rotating this curve the other way, increasing its resistance, right? Yes?
Sorry, could you start writing bigger?
Oh, yeah, sure. So this is R1, and this is R2. Is this good? So for a switch, when it's open, we want to go more toward the vertical axis. When it's closed, this line should go more toward the horizontal axis. So regardless of the voltage, the current is 0, or the case of extremely high resistance. The diode does both of these. And it does it not in such a perfect way that the ideal switch does, of course. And it does so, it does half of it on one side of the voltages, the other half on the other side. So for the diode, I'll draw the diode characteristics. The diode is more like this, something that has a very, very, very low resistance on the positive side and a very, very, very high resistance on the negative side of the voltages. So, and this is a simplified view, but I'm trying to show the general idea. So essentially has very low resistance when the voltage applied to it is positive, and very high resistance and the applied voltage is negative. This is, like I said, this is a simplified description. A simplified and limited description. Okay, but so the blue curve that I have drawn here corresponds to, essentially at a sort of high level look, is the IV characteristics of a diode. Now, if you have something like this, think about the circuit that we discussed before. If I have that input voltage being the sinusoidal voltage that we just talked about, and this is how you show a diode. And if you put this capacitor here, imagine the capacitor is initially uncharged. As soon as the input voltage rises a little bit, you're putting a positive voltage between the two sides of a diode. And the direction does matter. You have to pay attention to the schematic. You see it has an arrow. And that's the direction in which it would like to show low resistance or pass a high current. As soon as that voltage indicated here becomes a little positive, that diode shows very, very low resistance, acts like a closed switch. It's essentially in this region where V is a little positive. So that capacitor would get charged because this is the switch that's closed. Now imagine the capacitor has reached the maximum value, V0, and this input signal has reached its peak. Now it starts decreasing. Well, now the left side is at a lower voltage than the right side. So the diode has a negative voltage based on the polarity I've indicated. So now it is going to be on this side, a negative voltage. So it will allow very, very little reverse current, extremely small. Right? So essentially acts like a an open switch. And so this would be a basic circuit that you call a rectifier, because it takes a voltage and an input that has both positive and negative sides and chops off the negative side. Okay, so again, we will talk about this in great detail. But what I'd like to do now is to zoom in a little bit and tell you a little more about the exact shape of this, the IV characteristics of this element, the diode. Okay, so as I just said, the schematic of the diode is like this. And like any other element that we work with, we have to assign a polarity to the voltage and current. And conventionally, this is the voltage that, this is the voltage polarity that we assign. And this is the current direction that we assign. Again, you could, of course, choose other polarities, but then you have to remember that those are the negatives of this. And so you would, it's better to go with this convention to avoid confusion. And this is what the IV characteristics actually look like in greater detail. So this would be V, and this would be I. This is the actual shape of the IV characteristics of a real diode. Does anyone know how a diode is made? No? So I'll tell you the five-second version. There's this thing called a semiconductor. And that's a material that, that you can add impurities to change its electrical conductivity greatly. So we have insulators and we have metals. Insulators don't conduct electricity, and conductors do, right? There is this thing called a semiconductor, and based on the amount of impurities you put in it, it could have a high conductivity or low conductivity. And you can put two types of impurities in this. And that gives it a sense of polarity. So you can create what you call an N-type semiconductor, something that has impurities that add more electrons to the system. You can create a P-type semiconductor, something that has impurities that constrain electrons or steal electrons from the system. And if you put these two together, you will form a diode, because you create a charge distribution in space that will block the flow of electrons. And it will behave very differently if you apply a voltage one way versus the other. Again, if toward the end, if we have more time, I can tell you more about the physics of this. But of course, if you're interested, you can take courses like 315 or 415 later, or even go on to take some solid state physics from the physics department. That's what it looks like inside. As far as the circuit is concerned, this is what it looks like. Now, let's give a sense of numbers here. So as you can see, if I start increasing the voltage a little bit, initially it's reluctant to let current go through. Initially, it grows relatively slowly. But beyond a certain threshold, it picks up quite rapidly. And then it becomes very steep. And this is where it really acts like a very low resistance, like a switch that's on, like what we had on that, like that blue graph there, right? Now, where does this happen? How much voltage do you need to give it for it to start being very favorable to the passage of current? Does anyone know how much voltage you need for a typical diode? It's of the order of half a volt Of course, it varies from device to device. A typical value people would quote you would be 0.7 volts. So this is something you might say, if I were to mark this threshold by extrapolating this slope, this would be somewhere, let's say roughly in the 0.5 to 0.7 volt range. So I should write this bigger. And then that slope is very steep, so it corresponds to a very small resistance. It could be maybe a few ohms or a few tens of ohms. So if you want this diode to act like a good switch that's closed, it won't work if you just give it 0.1 or 0.2 volts positive. It will allow very little current. But as soon as you hit these values, then it will start rising. Now, this reverse current, on the other hand, so if you give it a negative voltage, you will see that it does give some current, but it's a small amount. For many applications, you want this amount to be really small. Because if you think about the switching behavior that I just described, ideally you would like this to be 0, right? Not have any current on this side. So that, again, depends on the exact design of the diode. But it could be really something very small, indeed. You know, we could be talking picoamps, nanoamps, depending, again, on how large it is, what material is made of. OK? So this is a very small current. Now, something interesting also happens way out here. So if you give the diode a big negative voltage, so if you keep, so you apply this negative voltage to it, and you keep increasing the value of this negative voltage, it will behave the way you expect it to up until a point. Beyond that, it will say, I can't take this anymore. I'll let current through. It's literally like that, right? And this is where you say a breakdown has happened. So we call this the breakdown region. Now, the physics of this breakdown, there are different mechanisms. Has anyone heard of a Zener diode? So Zener diodes, which we will talk about again, but there's the Zener breakdown mechanism, of course. But there is more than just that, even in Zener diodes. There's, for instance, avalanche breakdown is another important mechanism. But anyway, so the breakdown implies that it loses that basic diode property that you were expecting almost no current in the reverse region. Now, sometimes this breakdown could be destructive because imagine here this could be potentially a large negative voltage. So you're applying a high voltage across the device. And this current can grow very fast. So the power in the device can be very high, and it could just destroy it. And it could go out of control. You could also have diodes that within some range of current, this breakdown in them is reversible. So it doesn't destroy the device, that you can actually operate here. And that's what you use Zener diodes for. And that's a very useful feature that we'll talk about. But so to maybe label these, so this is, when the voltage is positive on this side, we call this the forward region, or the diode is on. This is forward bias, or the diode is on. The negative voltage range is reverse bias. diode is off. And well, technically, if it's in breakdown, it's not off anymore. So it's allowing current in the reverse direction. So maybe I'll put this diode off. Although the breakdown is still reverse bias, but it's not necessarily off. So let's say this is maybe where the diode is off. But often you would see this definition of diode being off extended to all negative voltages. So maybe it's good to specify exactly what one means. Okay. So all I have to do to enable you to solve a circuit that contains diodes is to give you the element relationship. Because remember, to solve a circuit, you needed KVL, KCL, and element relationships. For a resistor, V equals Ri. For a capacitor, I equals C dV by dt. For an inductor, V equals L di by dt. For a diode, this is the relationship between V and I. It's not as nice and compact as it was for some of the other elements, but it's a known relationship, right? And I can, in fact, give you formulas that describe at least different regions on this graph. But you could imagine that I could also give this to you numerically. So I could just give you a lookup table of I versus V. And you would have everything that you need for the diode. So I'll start by, in principle, we could say that that's it. We finished, right, the topic of diodes. Because the rest is applying your KVLs and KCLs and this element relationship. In practice, of course, we would like to gain some experience with how this behaves in different circuits, right, and build insight. And that's what we are going to do. Anything you guys would like me to elaborate on here? So let me give you the formula that describes a good chunk of this curve. The current as a function of voltage is essentially this. Some parameter times an exponential of V over what you call a threshold, a thermal voltage. And that's, have you guys seen the Boltzmann constant in first year physics? Does KT ring a bell? What is the value of KT at room temperature? Boltzmann constant times room temperature, which is 300 Kelvin. That's a useful number to know. It's about 26 milli-electron volts. Or maybe it's more comfortable for people to say about 25 milli-electron volts at room temperature. That's what you have here. That's the KT, or that thermal voltage. So this is the Boltzmann constant. This is absolute temperature. And there is sometimes this. This N is called an ideality factor. And it's something between 1 and 2, maybe, for a lot of diodes. Often in a simplified model, you might not see it. In the simplified diode model, it may not show up. Okay, so N typically around 1 to 2, let's say. Again, none of these is set in stone. It's about 26 milli-electron volts at room temperature. And it's like this. Now this IS, I'll write it here. It's called the reverse saturation current, and we'll see why in a moment. And it would really vary, but in general, it's something very small. So say it could be, for instance, in the tens of picoamps range. Oh. A very small value. For example, in the picoamps. But again, it varies from device to device. Could be smaller, could be larger. Now, if you try to plot this, this would be a nice exercise if you wanted to do it at home on your own. This would give you good insight. Just plot this in Excel or MATLAB or what have you. Just take a sweep of voltage from some negative value to some positive value and plot this curve for some typical parameters that I have listed here. And you will see, indeed, that it will look like this, because it will look like what we have up here, with the exception of the breakdown region. The breakdown is not included. Why? Because consider the formula. So if you apply a small positive voltage, so imagine you have applied 0.5 volts, right? You're dealing with exponential of 0.5 volts, which is 500 millivolts, divided by 26 millivolts. I should say millivolts. We have already divided this by an electron, millivolts. So 500 divided by 26, let's say, right? So that's a factor of what? 20, roughly speaking. So you're talking about exponential of 20. That's a very large number, right? It's already a large number. And in fact, that -1 next to it is inconsequential. Now, IS is a very small value, but multiplied by the exponential of a large number, it becomes something substantial. And you see that the growth is exponential, hence this very steep rise on the positive side, as you see it here. That's what you see on the positive side. On the negative side, imagine you apply a negative voltage, negative V. Well, so you're dealing with the exponential of a negative number, right? And you keep increasing that negative number. Well, the exponential of a negative number, growing negative number, it's just extremely small, right? So the exponential term actually vanishes next to the the -1. So what you have in parentheses effectively reduces to -1, approximately. So the current becomes equal to approximately -IS, which is a very small value. And that's what happens in the reverse mode. It's an almost constant, not quite, but an almost constant -IS. Up until breakdown happens, and that could be a very complicated phenomenon. It's not captured in this formula. So the diode IV equation from a simplified model and one which does not include breakdown. But it's now, admittedly, this is not as simple as V equals Ri or I equals V over R. This is a much more complicated element relationship. But it is an element relationship nonetheless. So you have an equation that relates I and V. Instead of one parameter like R, you have three parameters, I, S, N, and VTH. But I and V have a well-defined relationship. And so together with your KVLs and KCLs and this, you can solve a diode circuit. Now, depending on your interests, this could be a very fun exercise or a painful exercise, right? Now, even if you find it fun, you might find it not very practical. Imagine you have a circuit with 10 diodes, each of which has a voltage and a current, and they're all connected with a bunch of other elements, resistors and capacitors and so on. And you're writing your system of equations, KVL, KCL, or if you're using nodal and mesh analysis. And inevitably, in the system of equations, the element relationships show up. So you have, for each diode, you have a relationship like this, a highly nonlinear equation. And you have to now solve this system of coupled nonlinear equations. And that's not very practical, especially if you're trying to design something. So you're trying to gain insight and from an architecture point of view, trying to see how putting diodes in different parts of the circuit could affect the behavior so that you can design something. And because of that reason, people simplify this behavior further. So let me maybe just highlight this. Okay. So what we will talk about after a short break is how to take this and further simplify it so that we can do things much more quickly with diodes in circuits, as long as we are comfortable with approximate behavior. Okay? So let's take a 5-minute break. I think we can start the second half. Sorry. And what I'd like to do now is to take this, or equivalently this, and simplify it a little bit progressively to something that we can deal with a lot more easily in circuit. So simplifying the diode IV characteristics further. So let's start with this. First of all, very often, not always, as we'll see maybe later this week, or next week, very often we are staying away from the breakdown region. So very often we are interested in the range of voltages that are slightly positive or negative to the point that they don't lead to breakdown. Now, one simplification would be, for instance, to just neglect the fact that on the negative side that there is a small current. Let's say if we don't really care, if this is on the order of, let's say if all our currents in the circuit are in microamps and milliamps, and then the reverse current is picoamps, maybe we don't care about that. We could say that's approximately 0. Okay. So one simplification would be to do something like this, to say in the reverse mode, there isn't much happening. I guess I have to draw this a little bigger. To give us room. So I'm zooming in, so I'm exaggerating this. Okay. So one simplification would be to say, well, let's neglect that reverse current. So this is approximately 0, or we assume that it's basically just 0. It tends to be a very good approximation for many applications. But you might also say, well, that's good, that's a simplification, but I still have that exponential dependence, that nonlinear formula for the forward region. How can I simplify that further? Well, this is one thing that people do. Take the behavior of this very steep rise and just extrapolate it. Okay? Extrapolate it to a point that crosses the voltage axis. And do this with a straight line. Okay? And so say that the IV characteristics are basically like this. So you are really just throwing away this little part. Okay? And like I said before, this value, this intersection point, would be something on the order of 0.5, 0.7 volts. So let's say approximately 0.7 volts. Okay? And say that basically instead of having that nonlinear behavior, that exponential curvature, the diode just has a piecewise linear behavior where its current is 0 if it's under a negative voltage or a slightly positive voltage, up to a point where beyond which the current will just increase with a constant slope. So you have basically taken that curved behavior of the diode and broken it to approximately 2 lines. So this is called a piecewise linear approximation, because each piece of it you've taken and approximated it with a line. So I'll add this here. So assume that the reverse current is 0, and that this behavior continues this behavior, which I mean 0 current, continues even into positive voltages up until a certain threshold. Which could be, let's say, approximately 0.7 volts, depending on the device. And then, beyond that, you have, again, a straight line increase in voltage. Beyond that threshold, assume a linear, increase in current, not voltage. Increase in current as a function of voltage. So with a constant slope that matches the actual behavior of the device asymptotically. So this is it. Basically, it's a straight line and then another straight line. And this one would have a small slope. Or sorry, a large slope on the I versus V, or small in the reverse way. So as corresponds to a small resistance, for example, let's say a few tens of ohms. Let's say 10 ohm, just as an example. Again, it would depend on the device. So this is basically what you have done here is a piecewise linear approximation. Okay. You might even not be satisfied with that. You might say, oh, this is still too complicated. I have to kind of worry about this slope. But if it's a very small resistance, if I have a circuit that has resistances of kilo ohms in it, if the slope of this increase corresponds to a 10 ohm resistance, why do I care? Maybe I'll just assume that that resistance is almost zero. So another simplification would be where you take the same thing. Now I'll use a different color for it. You'll use the green. So you do the same thing, and you have that. But then here, you assume that it's a straight up line. Neglect that small resistance in forward bias. So this corresponds to a zero incremental resistance. Here I'll say a small incremental resistance because it doesn't start from the origin. So that's the simplification number 2. So now it's even simpler because all you need to know to recognize this element or to be able to use it is this value, be it 0.7 or 0.6. If someone tells you I have a diode that's essentially like these two straight lines and its turn-on threshold is 0.7 volts, you know everything about it. Would anyone like to suggest a further simplification? Be bold. Yeah, get rid of the 0.7 volts too. That's the power of engineering. Right? So still the same in the reverse part. So simplification 3 gets rid of that. Assume that threshold voltage is 0, essentially. So you have the red curve as the IV characteristics of this device. This device is called an ideal diode. And these progressively add up, right? So simplification 2 was the above plus. And simplification 3 is, again, the above plus. So by now, you have an ideal diode. This ideal diode is basically that switch that we talked about at the beginning, that if you wanted to operate in the forward mode, it would be like a switch that's closed. So basically, it can allow any current in the forward direction. And let's go back to our reference schematic here. Can allow any positive current in the forward direction, forward meaning where the current is positive. And essentially, your voltage, instead of realizing that it's slightly positive, you say, well, it's essentially 0. It's a very small amount, so I'll neglect it. So it's like a switch that's closed. And in the reverse part of the curve, when you apply a negative voltage, no matter how negative, the current is 0. So this is the ideal diode. Now, working backward, you can also build these other two models based on an ideal diode. Imagine I give you an ideal diode, so something that has the red curve. Can you do something? Can you add something to it to make something that has the green curve? Add a voltage source, a 0.7 volt voltage source to it, a battery, in series. So now assume you have an ideal diode. And there isn't a particular schematic for it. It's the same. Of course, one has to explicitly talk about, now, if you talk about a diode, let's say in a problem or something you're trying to design, if you're referring to an element, you should describe its IV characteristics. So you might say, this is an ideal diode, right? If you have an ideal diode and you want to, so red characteristics. To go to the green characteristics, take your ideal diode, add a small battery to it, put the whole thing in a box, So let's say this is a 0.7 volt, and this is ideal. If you look at this I versus V, this will be the green curve. Because the ideal diode, when it's on, when it lets current to go in the forward direction, it takes 0 volt drop. So this little battery adds that 0.7 volt drop. Whereas if this V, which is across the entire thing, if it's less than 0.7, you see that the ideal diode will have a negative voltage across it, so it will not allow any current. So this is a good exercise at home. So verify. So verify this. That this circuit gives you the green characteristics. How about that? Okay, so do that as a little exercise at home. Now, what if I wanted to make it one step more sophisticated and get the blue characteristics? What should I do? No, to get the blue behavior here. Add a resistor to it. So this is to go to the green characteristics. To go even further, to get the blue characteristics, take what you've done, an ideal diode, add that little 0.7 or whatever you need, volt battery, and then some resistance. Let's say we said in our example maybe 10 ohms. So now if you plot I versus V, V being the entire voltage drop across the two terminals coming out of this box, this will behave like this blue curve here. And again, as a very useful exercise, verify. That you get the blue characteristics. By blue, I'm referring to the curve on that graph we had up there. So very often you will see a diode modeled, a real diode modeled like this. Now this has, of course, you have thrown away this little part of the graph, this curvature here, as well as the actual reverse current. But again, this could be a very good approximation. But by sacrificing that amount of detail, now you are you're dealing with an element that's essentially a switch, on or off, depending on which side you are in. Something that you know how to deal with in the past, switch, close or open. Plus a small voltage source, a fixed voltage source of 0.7 or whatever, plus a small resistance. So circuits that you have solved before. And so there is tremendous power in these simplifications. Because now all of a sudden things become very familiar and very easy to handle comparatively, right? Of course, now you might say there's always the fundamental difficulty of dealing with the diode, even for the ideal diode, the red curve. how do I know when I have a diode in a given circuit? How do I know if it's operating in the forward mode, forward bias, where the voltage is 0 and the current can be anything positive, or the reverse mode, reverse bias, where the voltage is anything negative and the current is 0? Even for an ideal diode, it's not just one line. It's two lines, right? And I have to know if the diode is essentially on or off. And depending on whatever else is going on in the circuit, the diode could be in one or the other state. So there is that fundamental challenge always, no matter how much you simplify. So for instance, if you have a circuit that has 3 diodes in it, even 3 ideal diodes, if you think about all the combinations of each diode being on or off, how many possibilities are there? 8, 2 to the power of 3. Each diode can be on and off, on or off. So that circuit is essentially in one of 8 different possibilities. How do you know which one? You have to solve for all 8. There will be 7 out of those 8 that once you try to solve for the whole thing, 7 out of those 8 will give you inconsistencies. 1 will not. That's what the way nature finds its way. Okay. But you have to solve the 8 circuits. So it could be difficult, quite intensive, right? Fortunately, of course, as you gain experience with diode circuits, you will start spotting trends. And of course, if you're trying to design something with diodes, then you will, of course, already have some insight and know how to use it. But it's very important to build up to that insight. And so that means that you will have to do a few exercises where you do consider all these different possibilities and see how they would lead to something inconsistent, something that contradicts something else, and see why there is one situation that is all self-consistent. And then you will start seeing the trends. So I'd like to, if there's anything you guys would like to discuss here, let's chat more. If not, we'll take a look at an example. So let me write this down. Even for an ideal diode, how do we know in a given circuit whether it is forward or on or reverse or off? The answer is we have to try all possibilities. And find the one where everything is consistent. So if you have 5 diodes, that would be 32 possibilities. So example. Let's say you have a voltage source here, 5 volts. I have a diode here. Another diode here. maybe another diode here. Let's say this is 2 ohm and 3 ohm. So assume ideal diodes and find the current I. So I assume all 3 diodes are ideal. So we have to try 8 possibilities. Possibility number 1. So let's call these D1, D2, and D3. Possibility 1, D1 on, D2 on, D3 on. If all 3 diodes are on, which means they are in the forward mode, remember the ideal characteristics: 0 voltage, any positive current. Right? Let's try that. If the voltage across them is 0 and they can have any positive current, I have to replace them with a closed switch, right? So I have a 5 volt here. I replace the diodes with wires, and so I have the 2 ohm and 3 ohm. Okay, what is the current I? 0, right? So I have 2.5 amps going here. I is 0. What is this current? 2.5 amps. Are we all happy? Well, diode 1, is it in the on mode? Is it in the forward mode? Its voltage drop is 0. That's good. Its current is also in the positive direction, you see? It's going in the positive direction. So diode 1 on, that checks out. Same for diode 3. What about diode 2? Contradiction, right? So this contradicts D2 on. Now, so let's try the next the next possibility. So let's say D1 on, D2 on, and D3 off. Right? I'm just doing a brute force kind of search. So D2 is still on, and D3 is off. So this basically is left open, right? Then I still have I equals 0. I still have 2.5 amps here and 2.5 amps here. Same problem as before. Because it's going in the reverse direction of D2. You see, if D2 is on, the current in it should be going from the lower end to the upper end, whereas the current is in our circuit is going the other way, so it contradicts. So let's go to possibility 3. So let's say this time D1 on, D2 off, D3 on. So D1 and D3 are going to be replaced by wires, but D2 is going to be replaced by an open circuit. So now what would this current be? Call it I. This would be just 1 amp. And how about this current? Also 1 amp. And how about this current? 0. Does this contradict any of the things that we saw? No. Actually, this is consistent with the assumption on all 3 diodes. Do I need to keep going? No, definitely not for this circuit. So maybe I got lucky, or maybe I used a little bit of insight to choose this, right? Because when I did the first one, where I did this, I saw that 2 things checked out. It was this diode 2 that was problematic, and that gave me a hint that maybe if I turn that off, maybe things could work out, right? I'm not saying this as a bulletproof guaranteed way. If you see, because depending on the complexity of a circuit, things could get confusing very easily. So I would still advocate, and the exercises you will be doing will have a handful of diodes. So I really advocate that you consider all possibilities and see how they contradict something, right? This is the best way to get the best way out of the examples you practice. But so this is the actual solution. But as an exercise, try the other possibilities and see if they all lead to some contradiction. But basically what you just saw is the general approach to solving a circuit with, at least with ideal diodes. Now imagine if I had said, these diodes are not entirely ideal. They are like, each of them are like an ideal diode with a small voltage source next to it, 0.7 volts, right? So if I had said they are like the green model here. Well, then in each of the possibilities, in each of the 8 combinations, you would, when a diode is off, you would still replace it with an open circuit. But if the diode is on, you would replace it with a short circuit plus a small battery of 0.7 volts in the correct direction. And then you would solve the circuit for that. If I had said, well, they are like an ideal diode plus a small battery plus a non-zero resistance, then you're going up to that more sophisticated model, where you have to, when you assume that a given diode is on, you have to replace it by a wire plus a small battery plus a small resistor, and then solve the circuit with that. So, of course, it will be a little more involved, but nothing new as far as solving circuits is concerned. Okay? So you'll have to practice these things, and I'll give you some exercises. But right here, you can take this and turn it into several different practice examples, right? What if you wanted to assume that these are not, that you're not happy with any of these models, that you actually wanted to include the IV characteristics of the diode, the actual exponential relationship? Well, you would, again, write the KVLs and KCLs and all that. For each diode, for the element relationship, you would include that exponential dependence, that formula. And you would solve the entire system of equations numerically, self-consistently. There's standard ways to deal with that. Again, you guys being many of you in software or interested in software, you could write a small code as an exercise to solve a circuit like this with an actual formula, exponential formula for the IV characteristics. You can even extend it further. You can go look up the characteristics of a diode from a data sheet from a company that sells you a diode, and they'll give you a graph. And you can just go select points on that graph and put it in a lookup table, use that in your code to solve for the whole system of equations. Those things are all doable, and in fact, they are done. When you look at a modern-day circuit solver, as an engineer, you might design a circuit using this kind of insight, with this kind of simplification, these models with various degrees of sophistication, because they would give you the general behavior. But once you have designed the circuit, and your circuit might have 20 diodes in it, now you want the exact numbers. You would put it in a simulator for which the computer has, the code has the exact models from the manufacturers representing the characteristics of each element, including the diodes, and would solve the system of nonlinear equations for all the unknowns. So these are all done routinely. And of course, they are done by nature automatically every time your circuit does something, right? So they're happening in your devices all the time. One other thing I wanted to, let's see, I think we are out of time, so we'll leave it at this. But next time, what I'd like to do is do that exercise that I promised, which is now take you through the steps of actually designing a power supply using this. So that's it. Thank you.